Folks, let's talk about a certain series of events during which, in this case, what we call a physical pendulum, an actual rod of mass m and length L, is released from the orientation shown and swings down through an angle of 90 degrees, and this rod gets to well, an omega max just before it collides with this object point mass of mass m that's located a distance d from that axis. And these things collide, and we get a new omega system, I'll call it. And then this system swings up through some maximum angular displacement theta max. All right. So, what I've done explicitly here is define 4 separate instants. All right, and that's part of analyzing one of these problems, is to say what are the important instants. All right, and I'm going to label these instants 1, 2, 3, and 4, and you really have to be able to discern when are the important instants. And here, why is this important? Well, because this is an initial instant where there's a maximum amount of something, and here there's a maximum amount of something, but here there's there are criteria that we can use to connect one instant and the next. All right, and in particular, the criteria from 1 to 2 is that this physical pendulum conserves mechanical energy. So I'm going to say ME1 equals ME2. All right, that's not an interaction between any objects. It's just the pendulum transforming one kind of energy into another. All right, and then from instant 2 to instant 3, well, that's an interaction between one object and another. All right, the physical pendulum and the point mass, and during that interaction, well, we have to say that angular momentum is conserved, and that angular momentum at instant 2 equals angular momentum at instant 3. Because in that, if we assume that not a whole lot happens to the angular displacement of this pendulum while the interaction with the point mass is happening, then we can neglect, any gravitational accelerations that make the... So if we say 2 to 3 is a nice short amount of time, then we can conserve that angular momentum during that interaction. And then from 3 to 4, what we now have is a system that does not involve any additional interaction between objects. The objects are now a system, and now this system, ME3, conserves mechanical energy again. Fair enough? So let's look at how each of these, how we can write the right expressions for each of these intervals or kind of transitions from instant to instant. Okay? Try to do this. Make this generally smaller. Let's group. Okay, so if we take this first set of this first one here and say, let's conserve that, let's apply that conservation of mechanical energy from instant 1 to instant 2. Well, this physical pendulum has some gravitational potential energy at instant 1, and it's not moving. And at the end, well, we can choose to say that this all turns into kinetic energy. All right? And in particular, this is a system that is not translating. It's not, every part of this object is not moving in one direction, but this object does rotate. So this gravitational potential energy turns into rotational kinetic energy. All right, now, the gravitational potential energy we're going to write as mgh. Well, but h of what relative to where? You have some choices there, but in this case, why don't we say that? Why don't we say that we'll call this lowest point height 0. So what height is the object at? You know what? That's actually maybe not the best place to choose, is it? Yeah, you know what? It's fine. That's fine. So let's say this. Let's say if that height is 0, well, what height is the pendulum at? We're lucky here that all of the pendulum is at height h. So fine, let's go forward with that, and you'll see a mistake an omission I've made in a second. But well, when we say h, we really mean height of the object. And the object, if we call it a point mass, where is that object? Well, it's at the center of mass, right? And that center of mass is, well, it's L, actually. It's height L above what we called height 0. Now, this KE rotational, we can say, is 1/2 I omega squared. But here's the deal. Where's the center of mass of the pendulum at instant 2? Well, it's right here. And that's not at height 0. So what we should really say now is there is still some gravitational potential energy of the system relative to where we're calling height 0. And so now we say this is the system, well, not the system, but the pendulum is located, its center of mass, is located at height L over 2. Fair enough? Now notice here that if we perhaps were to write an expression for how fast this is omega 2. Omega 2 is, I know it's small, but what we call omega max. What's omega max? Well, notice we would subtract this over to here, and the mgl minus the mgl over 2 is just mgl over 2. And that's 1/2 I omega 2 squared. And, well, what we should do is probably say that the I of that rod about its end is 1/3 m L squared, and then there's our omega 2 squared. Okay? So this is just almost like saying we could actually have called our height 0 at the center of mass of that pendulum, but we didn't. And that's fine. So algebraically, those will go. These are the same. What I should have used is capital M here. These are the same mass, so these can go. One of these can go. And pretty soon we get to a pretty nice expression for omega 2 is 3g over L. Well, that's nice. That's at least somewhat elegant expression for how fast that pendulum is moving in terms of angular speed at the instant just before it makes contact with that mass, little m. Okay? So, I mean, being able to apply a conservation of energy statement is a nice way to deal with this physical pendulum. There are other ways you can do a net torque statement, but you have to be able to integrate because the component of mg changes as the object swings. So energy, a nice way to tackle these physical pendulum kinds of questions. All right, so let's sort of put this result aside for a minute. Groupity group. Get out of the way. I'll put this over here. I'll put this in my, yeah, how about this? Let's look at instant 2 to instant 3. that over there. I'm sure we'll use that again at some point. Instant 2 to instant 3, we said, is a conservation of angular momentum, right? Which says, well, L2 is the angular momentum of that rod, that physical pendulum, just before it contacts the mass. Well, that's going to be I2 omega 2. And afterwards, we can say I3 omega 3. Now, this I2 is just I3 ml squared omega 2. Now, after the interaction, this is now a system of, different objects. So what we have is I pendulum plus I mass, and they do share the same common final angular velocity after this interaction. All right, so this goes 1/3 big M L squared. Omega 2, yep, we do have an expression for omega 2. I'll keep that in my back pocket for right now. Omega 2, and this is going to be the same, 1/3 M L squared. Now, the object we're calling a point mass, little m, it is located at d meters-ish, meters or whatever units of length from that axis of rotation. So there's its moment of inertia as a point mass, and here's the angular speed after that interaction. All right. How do what's there to simplify here? Not a ton, probably, maybe. I'll just say, if we wanted to, we could say, I wish I had done this in a different color, so I will do that now. That's ugly. That's fine-ish. So this now says that I'll take 1/3 m big L squared omega 2 divided by I system 3 ml squared plus md squared. Well, there's an expression for the angular velocity. Nice easy expression for the angular velocity of that system after the two object interaction. Okay there? Okay, and now let's put this in our back pocket, other back pocket, group, shrinkity-bink, this over, and then we can go from instant 3 to instant 4, and say that this system now, well, has some rotational kinetic energy as a system in the beginning, and that turns into some gravitational potential energy at the end. And I sort of paused for a minute there because I'm thinking about what's the easiest way to talk about how much potential energy, how much gravitational potential energy at what instant. And I think there's an adjustment that we can make, and I feel good that we can make it midstream here, and that is for this part of the activity, I'm going to change my height 0 to right there. Do I want to do that? What did I do? I still don't know that I want to do that. Okay, so I've been away for a few minutes. You can't tell, but here's the deal. Here's what you can do. All right. This we're gonna do what looks like simplify, but take into account what really matters. All right. What really matters here is that there are two different. There's a couple ways to address this. One is you can say that this system is can be simplified as a point mass located at that system's center of mass. I'm not going to do that. All right, what I am going to do is say that there's some, well, these are just two objects, each of which undergoes some change in gravitational potential energy, and we can treat them separately. All right, and so what we really are saying is maybe we say that this is there's a net GPE at instant 4, and there's a net GPE at instant 3, and I am saying that KE rotational at instant 4 is 0. So what we really care about here is we can say that KE rotational at 3 is, well, the change in the net gravitational, what do you call it, potential energy, all right? And that means that KE rotational at 3 is delta UG of the pendulum plus delta UG of the point mass. All right? And then we say, well, this is 1/2 I system omega 3 squared is, well, this is going to be mg delta h of the pendulum plus well, sorry, I should say big M because this is our pendulum, little m because this is our mass, delta h mass. All right, and then the question is, let me stay with this 1/2. Well, I system we can still write as 1/3 big M L squared plus little m d squared omega 3 squared. You want to square this? Please be my guest. It actually probably doesn't come out that hairy because you'll have this I system term squared in the bottom and then one I system term squared. But you know what? I'm just going to leave it as omega 3 squared. Now, the question is, what are these delta H's? All right. How much does the pendulum's, quote, height change? Well, the pendulum's height really is about where its center of mass is and gets to. All right, and its center of mass starts here, and it ends, a little higher up, there. Right, and we can express, you know how when we usually do pendulum stuff for a assumed perfect pendulum that we'll say does swings from here to here, we say that this height relative to this height is, quote, if this is a height h and this is a height 0, this height h is L minus L cos theta. Remember that? Well, we're really saying if this is height 0, that's the change in height, L minus L cos theta, where L is the length of the pendulum. Well, in this case, the kind of length that we have to use is where the center of mass is. So this turns into, let me move this. You know what? I'm going to ditch this whole thing for a second, just explicitly write that UG pendulum is mg L over 2 minus L over 2 cos theta, which is just mg L over 2 1 minus cos theta. And similarly, the delta UG for the mass is little mg, and its delta H is d minus d cos theta. Excuse me. D minus d cos theta, or just little mgd 1 minus cos theta. So then you can say that our let's see, 1/2 I cis omega 3 squared is, well, these two delta U's added up. All right, so that's big M G L over 2, 1 minus cos theta plus little m g d, 1 minus cos theta. You can actually factor out that, well, a g and a 1 minus cos theta. But what we have now, at least, is perhaps a way that if we needed to isolate that theta final, that theta 4. This is really, I guess, theta 4, instant 4. Okay? You know, are we really going to jam all this stuff together algebraically and, like I said, square this and put it in there? That sounds horrible. But I will say that this right side, like I said, can turn into, we can take a g and 1 minus cos theta out of this. And in this first term, we're left with an m L over 2. And in the second one, we're left with little md. All right, and that's our 1/2 I system omega 3 squared. Okay, so we're getting closer to being able to isolate that cos theta if we wanted to, and find what that angle is based on the other stuff. You know, again, what are we trying to find in this question? I don't know. I don't care. What I do care about is that we're able to go through a process and say that there are a few instants that are important, right? There's the instant before anything's happened. There's the instant right before an interaction happens. There's an instant right after an interaction happens. There's an instant where, in this case, the height or that angular displacement gets to a maximum. And what techniques or what principles can we apply to connect one instant and the next, right? And that's where we got into here talking about using energy for one sort of transition from one instant to the next, and here talking about using momentum, angular momentum, to talk about handling that interaction from instant 2 to instant 3, and then going back to an energy thing to connect instant 3 and instant 4. So that's the hard part. Do you know what principles to apply from one instant to the next? Okay? Hope that helps a little bit. And for my folks, I'll see you soon. For my non-folks, fire questions at me if you have them. Okay? Bye. Bye.